These are your notes for series and parallel circuits. So we know that we can make a circuit by connecting a battery. We need a source of voltage. We need some wires to connect things, and we need some kind of a circuit element, bulbs, resistors, buzzers, some reason for them to do something. Okay, so you've already built this. If we have a series circuit, we connect those one after another. So we have a one path for current to flow. We notice that when we add a resistor in series, the current goes down, and we can observe that with light bulbs connected in series because we observe the brightness of one single light bulb connected and then the brightness of two light bulbs connected in series, and they both are equally dim as each other and dimmer than they were when it was just one light bulb. So adding a resistor in series causes less current to flow in the circuit. That implies that there must be more resistance in that circuit. So the reason we know there's more resistance is because resistance is one of the things that determines what current flows in the circuit. So more resistance means less current flows. For parallel, we've added these in branches or loops. So in this case, there's more than one route for current to get from the positive terminal of the battery. Conventional current flows from the positive terminal of the battery, the long line, to the short line. And there's two routes. You could either take the bottom route or the top route, the way this particular one is drawn. If we use our track analogy, then this would be that everybody has to go through the water station, but then there's going to be a fork in the road, right? You can either go through the woods or you can go, on the regular track. But then everybody comes back together and has to go through the water station again, or you get dehydrated. So for a parallel circuit, there are the runners that go through the regular track, and then there are the runners that are on the regular track for a while, and then they go through the woods and then rejoin everybody else. So both sets of runners have to go through the water station. Everybody has to go through the battery, but there's more than one route in order to get back to the water station. The runners that stay on the track the whole time or take that route never go through the woods. And the runners that go through the woods don't go through that section of track, right? They miss part of the track. So it's kind of like you have two currents flowing at the same time. You have the current that's going through one route, you have the current that's going through the other route, but they're just running together for some section of time when they go through the battery, because everybody has to go through the battery. So when you add a parallel loop, what we see is that the battery is actually having more current flow through it than it does when only one light bulb is there. And the reason that that happens is because each light bulb stays equally bright. When you build a parallel circuit, what you see is that if I just connect it, that where I just have one bulb, just like the drawing on the left for series, and then I add this extra branch, when I connect that last wire for that top branch or that top loop, the bulb that was in there the whole time doesn't change. It is completely unaffected by the fact that you have added another loop. And so that first bulb, the original route, has current flowing through it. And then when the last wire is connected for the top loop, it gets current flowing through it too. So what does that imply about the amount of current that's going through the battery? Well, it's the current that's been going through the first route the whole time. And in addition, also the current that is now going through the top route, because everybody has to go through the battery. All the current has to go through the battery. And so the odd thing here is, potentially odd, is that is actually decreased resistance. When you add a loop in parallel, the resistance of your whole circuit actually goes down. All of this is dictated by Ohm's law, I equals delta V over R. Remember that this is a cause and effect equation here. The I, the current, is the effect, and the cause are two things. There are two causes or determiners of how much current flows in the circuit. One is the electric potential difference, and that's joules per coulomb. That's the related to amount of energy, delta V. And the resistance of the circuit. So if the overall resistance of the circuit changes, then you're now dividing by a small number. That means you get a bigger number for current. And also just reasoning that out with the track and runners analogy. So what we need to be able to do then is think through what's going on with current and resistance. We'll just kind of formalize this in an equation. For a series circuit, the current that goes through battery and the current that goes through bulb 1 and the current that goes through bulb 2, that's all the same current. There's only one route, right? If this is the runners on the track, they only have one way of getting around to the water station again. So there's only one current. It's the same amount of current. Once you've measured current anywhere in a series circuit, it's the same everywhere. I don't have to move my ammeter from the left side to the right side or between bulb 1 and bulb 2. Current is not used up in a circuit. That would be violating the law of conservation of energy. There's only one current. However, the electric potential difference of the battery, let's say that's 6 volts, then our current has a lot of energy. It's positive conventional current when it's at the positive terminal of the battery, and it has to lose all of that energy. Now, it's not really lost, of course. It's just converted to another form, heat, light, something like that. So my positive conventional current has a lot of energy at the high potential at the positive terminal of the battery. It's got to get to 0 when it gets to the negative terminal of the battery, because if it had any energy left over, then you'd be like spiraling up in energy every time the current goes through the circuit, and that would be violating the law of conservation of energy. So you got to lose all of the electric potential in one trip around. So if we kind of graph the electric potential, it goes up when the current goes through the battery. Going through a wire doesn't cost us anything. I lose some of my energy when I go through the first bulb, nothing for the next wire that connects, and I lose the rest of my energy when I go through bulb 2. So if this is a 6-volt battery, then this number is 6 volts, and then I would have to lose 3 volts. So that would be up by 6, down by 3 volts, down by 3 volts, so that I've lost all of my electric potential in one trip around. Otherwise, I'm violating the law of conservation of energy. That's not going to happen. So one current, but the electric potential difference across the battery is not the same as through each bulb. And this is only true that it'd be 3 volts and 3 volts for each battery if they're identical batteries. If they were different batteries, then maybe you lose 4 volts in one and 2 in the next, or 5 in one, or any combination that gets you to 6. For a parallel circuit, of course, it's different. The current through the battery is actually the sum of the current that goes through the first route and the current that goes through the second route. So notice these junctions that we have here. We have a splitting off point, or we have a place where the current has to make a decision. It doesn't really make a decision because all this happens at once. But if you kind of model this with like your runners on the track, you could kind of think of it as if it's making a decision. So if you're a runner on the track, you've gone through the water station, you've got lots of energy, but now I get to a fork in the road, and I have to decide which way am I going to take in order to get back to the water station again. There are 2 routes, and even though the wires are longer for that top route, that doesn't matter. All that matters is what is the resistance on each route. So from junction to junction, there's 2 ways to get from the place where the current divides to the place where the current gets back together. So that means that the current that goes through the battery, some of it goes through the bottom route, some of it goes through the top route. Everybody comes back together at the junction on the right. Because the current that goes through bulb 1 never goes through bulb 2, the same rule has to apply, that I have to lose all of my electric potential, all my energy, in one trip around. So the current that goes through bulb 1 never touches bulb 2. It doesn't even know bulb 2 is there. So all it does is its own little bottom loop. It's getting its energy pumped up by the battery. It's going through a wire, doesn't cost anything. I only go through bulb 1, so I got to lose all my energy in bulb 1. If I'm the current going through bulb 2, then I have to get my energy pumped up by the battery, go through a wire, and go through bulb 2. I never go through bulb 1. So I don't lose any energy in going through bulb 1 because I never touch bulb 1. So each of these is doing its own thing, kind of individually. So what that means is if I am the current that goes through bulb 1, My electric potential difference when I go through bulb 1 is the same as the battery's. My electric potential difference, my decrease in electric potential when I go through bulb 2, if I'm the current that goes through bulb 2, is the same as the battery. So you can write these equations in your notes, and I encourage you to do that in the drawings, but if you haven't thought through what's happening, the equations won't help you. There's you need to have them written down, but you need to think through what's happening on as I'm picturing these charges moving. Okay, so we have a calculation that we're going to do here, and it's called equivalent resistance. So equivalent meaning equal. So we think of this as what is the one resistor that I could take out these circuit elements, these bulbs and wires and stuff, and I could put in this one resistor, and my battery wouldn't know the difference. My battery would have the same current going through it. It's like, if everything was behind a curtain and the battery just knows, hey, how much current's is passing through me. It doesn't obviously have sentient thought, but then it would cause the same amount of current to go through the battery. So we have to calculate equivalent resistance. The reason we do this is because it'll tell us how much current flows in the battery. We have to calculate them differently for series and parallel, of course. For a series circuit, as you could imagine, we just need to add up all the resistances because more resistors causes less current to flow. So adding resistors in series will just increase the equivalent resistance, and so the battery is effectively attached to more resistance than it would be if there was just one of those. But parallel has to be different. For parallel, it's inverses. These are they're 1 over all of these things. So it's 1 over the equivalent resistance, comma parallel. So Req, comma parallel. And it's 1 over R1 plus 1 over R2. And the way math works, you cannot just get rid of those 1 overs. You won't get the same answer. And you'll be able to tell. Each fraction or term there, terms are separated by a plus or minus sign. Each fraction or term is a route to get from junction to junction for parallel. For parallel, it's not how many bulbs there are. Sometimes it works out to be the same thing, but it's how many paths, how many routes to get from junction to junction. For series, it's relatively straightforward. If I've got a 10 and a 20, add them up, I get 30. My battery would have the same current flowing through it if it had a 10 and a 20 in series or a 30 just all by itself. For parallel, though, what you'll see is that the equivalent resistance that you get for parallel will always be less than any of the individual routes. And you'll see that because adding loops in parallel actually decreases the resistance because what does it do? It makes more current flow. So let's see what this looks like. If we do this for a 10 and a 20 connected in parallel, we see that there are 2 routes. If the current takes the route to get from junction to junction that goes through the 10 ohm resistor, then it encounters 10 ohms of resistance or 10 ohms of difficulty as it goes from junction to junction. So that's 1 over 10. If it takes the top route, even though it's longer wires, that doesn't matter. Even if it takes the top route, it just has to go through 20 ohms of resistance. So 1 over 10 plus 1 over 20. Now you can get common denominators. 2 20ths plus 1 20th is 3 20ths. And then to solve for REQ, I will warn you that quite often people will leave this at 3 over 20 for the answer. And they'll do that if they don't keep tracking their variables on the left side of the equation. What you're doing on the right is finding right now what 1 over R is. That 1 over R does not change into R without you doing something. So if so track your equal signs down, write everything down, write down both sides of your equation as you go. 1 over R equals 3 over 20. So in order to get the R out of the denominator, you can just flip both fractions. So that would mean R over 1 equals 20 over 3. And R over 1 would just be R. And then make that into a decimal if you like. You can leave them in fractions, I don't care. If you're not a big fan of common denominators, the calculator way to enter this is just type in 1 over 10 plus 1 over 20, all in one line, hit enter. You don't need any parentheses or anything else. 1 over 10, the original equation, 1 over 10 plus 1 over 20, hit enter. It'll give you a decimal answer that doesn't make any sense. All you have to do is hit the x to the negative 1 button. And because x to the negative 1 is 1 over x, all that does is flip. It just finds the reciprocal of what you have. And then hit enter. If you have some other calculator method that makes sense to you, as long as you get the right answers, fine with me. This is a way that I do it in a calculator if I'm not doing common denominators, but make sure that you have checked these calculations multiple times, and the test is not the first time that you are trying to put this in your calculator. What this tells us is that if I just take out those 10 and 20 that are connected in parallel, and instead I connect a 6.7 ohm resistor, some little tiny resistor that has 6.7 ohms of resistance, my battery wouldn't know the difference. I'd have the same current through my battery as the battery experienced with the 10 and the 20 connected in parallel. Notice that 6.7 is less than 10 and less than 20. Okay, big, starred, important point. The battery is not, as we have seen, a source of constant current. The battery does not have amps printed on the side of it because it does not always have the same current flowing through it. The battery has volts printed on the side of it because it does provide a consistent electric potential difference for an ideal battery. The current that flows through the battery is determined by the electric potential of the battery, the electric potential difference of the battery, but importantly for us, what you have hooked up to the battery and how it's all attached. Is it in series? It is in parallel? What resistors, what bulbs do you have in there? All of the current must go through the battery to get its electric potential related to energy increased again. Another thing that we'll calculate here is this is probably the most common thing that you've heard for things that use electricity or electrical circuits. It's interesting. I do not know why that's on there. Is power. Let me go back. There we go. Is power. Power is expressed in watts, which is a joule per second, and you can calculate it any of these three ways. You don't have to use all those, just use whichever variables make sense for yours. Power is current times the electric potential difference, or it's current squared times the resistance of that circuit element, or it's the electric potential difference squared over R. Those are just putting in Ohm's law and to manipulate for other variables. So capital P equals 60W, you would read that to yourself as power equals 60 watts. And so if you know those values, you can find the answer.